Hello, so this is lecture 5, and we will be covering the last concept in our first chapter on oscillatory motion. So what we have discussed so far is simple harmonic motion, and in particular, we focused on the mass spring system. And we mentioned that the other system we will study is the pendulum. So this is what we are going to study now. So the pendulum, what is the pendulum? So the simple pendulum consists of a mass M suspended by a massless string of length L. Okay, so we say a massless string, that is the string is so light. So the only mass we care about is the mass of the particle suspended from the string. Okay, but the string has a length L as shown in this figure. Okay, so what we do is that we move this mass by this angle, for example, theta maximum, and we allow it to swing. Okay, so it will be swinging between minus theta maximum plus theta maximum, minus theta maximum plus theta maximum. In a minute, we will prove that the type of motion it encounters is indeed simple harmonic motion. But before that, we will do some Newton's second law. So the tangential component of the gravitational force, so this object over here is swinging due to gravity, as a matter of fact, okay? So this mass over here has the weight, which is mg, okay? And this mg has two components, one along the tangent of the oscillation, and one is along the radius over here, which we call centripetal over here. Okay, so it has two components. Now, how do we find the two components of this vector over here, which is mg? So we take this triangle. We take this triangle over here, this triangle. Okay, and we have angle theta. And we say, okay, let's take cosine theta. Let's take cosine of angle theta. It's equal to adjacent side over hypotenuse. Okay, so this is angle theta over here. What is the adjacent side? The adjacent side is this side, which we are calling the centripetal. Okay, so it is this side. So cosine theta. And the hypotenuse of this triangle. This triangle is 90 at this angle. Okay, and the hypotenuse is this thing, mg. So the adjacent side that we are interested in, is mg times sine of theta. This is how we found that. Times cosine. Yeah, so cosine. So the adjacent side that we are interested in is equal to the hypotenuse, which is mg, times cosine of angle theta. Okay, and this is why we got this side over here to be mg cosine theta. Similarly, if I take the opposite this time, so if I remove all these things, and now if I take the opposite, thing, so if I take now sine theta, this is equal to opposite side divided by the hypotenuse. Okay, so I got the opposite side equal to the hypotenuse, which is mg, times sine angle theta. And this is how we got that this side over here is mg sine theta. So now, if I go to what's happening in the pendulum, the tangential component is mg sine theta, and the centripetal component or the radial component is mg cosine theta. Okay, now, if theta is positive, there is a restoring force directed to the negative. This is similar to what we encountered with the mass spring system. If theta is negative, there is something pulling it backwards. So there is something, the restoring force is toward the positive. Okay, now what is the equation for the centripetal force? This is in Newton's second law. Ft is MAT, right? And AT, that is the tangential component of the acceleration, is G sine theta. Okay. Or Ft is MAT. It is equal to, what did we agree? This the tangential component of the force is this thing over here, mg sine theta, right? Is this thing over here. Ft is mg sine theta. Why is it negative? Because if theta is positive, that's negative. If theta is negative, that's positive. That's why there is a negative sign over here. Now, by comparing these two equations together, MAT equal minus mg sine theta, we get, if we remove the m and the m, we get AT is equal minus g sine theta. So this is the equation for the tangential acceleration in the case of the pendulum. Let's continue. Does it have another equation? Let's continue. So now we have, but what is the centripetal acceleration? Here we have to remember from rotational motion, S, which is the linear distance, if we are moving by an arc, so the linear distance is L theta, okay? And the tangential acceleration is dv by dt, and that's d2s by dt squared, okay? Now, so A tangential is L, because here what is S? It's L theta. So it is L is a constant number, it just shows up here. And then I have to take the double derivative of the second derivative of theta. So A tangential is L d2 theta by dt squared. Now, instead of A tangential, I will put minus g sine theta that I got here. A tangential is minus g sine theta. So now I have L d2 theta by dt squared equal minus g sine theta, or I divide both sides by L, I get d2 theta by dt squared equal minus g over L sine theta, okay? For very small values of theta, that's when theta is less than 10 degrees or 0.174 radian. For angles very much less than these, sine theta is equal to theta, okay? And this is why here, sine theta, we put theta instead of it, okay? This only happens for very small values of theta, okay? Now let's look at this equation. d2 theta by dt squared equal minus g over L theta. Does this remind you of any other equation? Does it remind you of this equation? d2x by dt squared equal minus omega square x, right? And this is, we said, is the equation for simple harmonic motion. So now instead of x, there is theta. So x is replaced by theta. So this is the same equation. This is a differential equation, the same mathematical form as the mass spring system. This one we got in the mass spring system, where omega for the mass spring system was square root k over m. Here it has the same solution. Theta will be theta maximum cosine omega t plus phi, but the omega will be square root of g over L. Okay. And theta maximum over here is the maximum angular displacement, and it should be in radian. Okay. In this chapter, make everything be in radian. Even if they give you an angle in degrees, change it to radian. So we have the differential equation. We solve it. We get that theta of t is equal theta maximum cosine omega t plus phi, where omega, the angular frequency, is square root g over L. Okay, now if we have the angular displacement, if we have this equation at any time, then we can determine theta maximum and phi from the initial conditions, just as in the case of a simple the mass spring system. We said that we get A and phi. A was X maximum and phi using initial conditions. So same thing here. We use the initial conditions, which are theta at time equals 0 and theta prime or V at time of 0. Okay. Here you just have to remember these things, that V is equal L theta prime. Okay. That is L d theta by dt. And S, that is the linear distance, is L times theta. And V, which is the linear velocity, is L times theta prime. Theta prime here is nothing but d theta by dt. D theta by dt. Okay. And A, the tangential acceleration, A tangential, is equal L times d square d2 theta by dt square. That is the second derivative. Second derivative. V is the first derivative. Anyway, we'll get to this in a minute. Okay. Now, if we have the omega, which is the square root of G over L, so we agreed that omega is square root or radical G over L, okay? Then I can get the period. The period is 2 pi, right, divided by omega. So this will give me the period to be 2 pi over square root G over L, and this is nothing but 2 pi square root of L over G. Okay, so we get the period to be 2 pi square root L over G. Notice that the period doesn't have to do with the mass, okay? No matter what mass you are attaching, the period is not related to it. It's only related to the length of the string, okay? And now, so the angular position theta of t is theta maximum cosine omega t plus phi. I can get the first derivative and I call it the angular velocity, okay? Because this is, so usually I have position, velocity, acceleration. Okay, so usually I have position, velocity, acceleration. But if I have angular velocity, then I have, angular position, then I have angular velocity, and then I have angular acceleration. If this is theta prime, this is theta double prime. If this is theta, this is d theta by dt, this is d2 theta by dt squared. So theta of t is theta maximum cosine omega t plus phi. What is its first derivative? This is a cosine function. So the derivative of the cosine is minus sine. And this omega over here jumps outside. So I get minus omega theta maximum sine omega t plus phi. And this omega theta maximum is nothing but theta prime maximum. Okay, now I take the second derivative, just as I did with the x in mass spring system. I take the second derivative. Again, the derivative of the sine is a cosine. The omega jumps outside, so I have minus omega squared theta maximum, and this omega squared theta maximum is theta double prime maximum, that is angular acceleration, the maximum angular acceleration. Okay. And now if I want the linear velocity, so remember the linear velocity is L theta prime. So whatever here I have for theta prime minus omega theta maximum sine omega t plus phi, I multiply it by L. So I get here minus L omega theta maximum sine omega t plus phi. And this is here is the maximum. And then the tangential acceleration is L d2 theta by dt squared. So I bring this theta double prime and I multiply it by L. So I get L theta double prime, which is minus L omega squared theta maximum, and A tangential maximum is L omega squared theta maximum. Okay, Now there is the radial acceleration. This has the definition, AR is V square over L. V, if I want the maximum of that, I will put the maximum of the V. The maximum of the V is L omega theta maximum, but I have to square everything and then divide by an L, and then I get this equation. Okay, if I just want to get the A radial, the centripetal acceleration or the radial acceleration, V square over L, so I bring this V, which is minus L omega theta maximum sine omega t plus phi, I square it, and then I divide by L, and I get this formula over here. Okay, perfect. Now, the last thing about the pendulum has to do with the energy. What's happening over here? So, also here we have conservation of mechanical energy. But what are the important positions? The important positions are for theta equal to 0, that is at equilibrium. So at equilibrium, what happens? At equilibrium, there is no height. At equilibrium, there is no height. Implies there is no potential energy. Potential energy is equal to 0. However, there is maximum. So however, there is maximum kinetic energy. There is maximum kinetic energy, okay? Or let's say kinetic energy is maximum, implies V is maximum. So one is V maximum, one is the speed maximum. It's maximum at the equilibrium position, okay? So mechanical energy at the equilibrium position, it doesn't have potential energy, it only has kinetic energy. So it is half mv, but not any v, it is v maximum square. So mechanical energy at theta equal to 0 is half mv maximum square. But what is v maximum? We derived it in the previous slide. V maximum here. V maximum is L omega theta maximum. So I just plug it and I get that mechanical energy at equilibrium is half ml square omega square theta maximum square. Of course, you don't have to remember to memorize these things. You don't have to memorize them. You can always derive them quickly. Okay. Now, what happens at theta equal theta maximum? So at this particular position at equilibrium, we got that the mechanical energy is half mv maximum square. What happens at the maximum height? At the maximum height, that is when theta equal theta maximum, the mass is at rest. So V is equal to 0, but it is at an altitude h from the ground, so it has potential energy. And potential energy is nothing but mgh. Okay, now I need to get this h over here. This h over here, if I know the maximum length, okay, and I can subtract this x from here to here, then I can get this h. And this x over here, if I take this right triangle, so if I take this right triangle, okay, this is a right triangle, and I take the cosine of the angle theta, cosine of the angle theta, it's equal to the adjacent side, which is x, divided by the hypotenuse, which is L. So x is L cosine of angle theta. Okay, and now here mechanical energy is at theta equal theta maximum. Okay, so this is equal to mgh, right? And h is, so this is mg into h is L minus x, right? And this is equal to mg into L minus x, which we derived it to be L cosine of angle theta. So I have L in both of them, so I take it outside. So I have mgl into 1 minus cosine theta. And this is not any theta, this is theta maximum, because we said this is mechanical energy at maximum elongation. Okay, this is here H, not any H, it is at H maximum. So this is happening at when the bulb is at the maximum height. Okay, so I get mechanical energy equal mgl into 1 minus cosine theta maximum. Now for every other theta, so theta at the equilibrium is half mv maximum square. Mechanical energy at equilibrium is half mv maximum square. Mechanical energy at theta maximum is mgl into 1 minus cosine theta maximum. For every other theta, there are two components. For every other theta, there are two components, the kinetic energy and the potential energy. So I have half mv squared plus mgl into 1 minus cosine theta. It is not theta maximum anymore. This is equal to either mechanical energy at equilibrium, which is half mv maximum squared, or mechanical energy at maximum displacement, which is mgl into 1 minus cosine theta maximum. So you choose which one you want to use depending on what is given. Okay, now let's solve an exercise quickly to see that it's easier than what it seems. So I have a simple pendulum that has a bob, yeah, something like a mass of 0.2 kilograms. So I have mass equals 0.2 kilograms. So let me write this down. So this is the mass. Where is this? Here. So this is the mass. Okay. And 1 meter long massless string. So this is my L. Right? It is displaced to the right by an angle of 0.1 radian and then released from rest. So what is at time equal 0? What is the information I have? Theta equal theta 0 or theta initial equal what? It's equal to theta maximum, which is 0.1 radian. It's in radians, so I don't change anything. Okay, so I'm given theta initial, and I have that it's released from rest. So I have that V initial is equal to 0. So these are the initial conditions. Okay, so this is what I'm given in the question. So part A, calculate T. What is the formula for T? Over here, I summarized all the formulas. So it is 2 pi square root L over G. Okay, if they don't give me G equal 10, then I have to use G equal 9.8. So this is equal to times pi, which is 3.14, times square root or radical L is 1 over 9.8. And I get the answer for this to be 2 seconds. Okay, and then we need to calculate omega. I have two ways to calculate omega. Either I say omega is square root of G over L. So I can directly do this. So this is square root of G is 9.8 over L, which is 1. And this gives me 3 points. This gives me second square root radical 9.8. This gives me 3.13 radian per second. Okay. Part B. Calculate the mechanical energy of the system. So since I have what is happening at time equal to 0, so mechanical energy of the system is equal to the mechanical energy at maximum displacement. Why is so? Because I have isolated system. So mechanical energy at any time is constant. Okay, so this is equal. What's happening at maximum displacement? At maximum displacement, I don't have kinetic energy. I only have mg h, right? Where we agreed h is L into 1 minus cosine of theta maximum So this is equal to M is 0.2 times G is 9.8 or 10, it's okay, so 9.8 times L is 1 into 1 minus cosine of the angle, which is 0.1 radian. So make sure your calculators are in radian. Okay, and this will give me 0.2 times 9.8 times 1, and then you open brackets 1 minus cosine 0.1, and you get the answer to this. (9.8) times 10 power minus 3 joules, which is approximately, you can just put it in approximately 0.01 joules. Okay, so that's part B. Part C, let's do it over here. At what angle or angles theta, so theta equal how much when the kinetic energy is equal to the potential energy? So here we have to say that the mechanical energy, we have to say that the mechanical energy is conserved. So the kinetic energy plus the potential energy is equal to the mechanical energy at the maximum displacement, which we have just calculated it to be 0.01. Okay, so I will plug it over here. But now what is the kinetic energy? So they are telling me that the kinetic energy is equal to the potential energy. So I will say potential energy plus potential energy is equal 0.01, or 2 potential energy is equal 0.01. By the way, potential energy, sometimes they call it GPE, sometimes they call it PE. Now they're calling it UG. So you just stick to whatever notation it's given. So UG is equal to 0.01 divided by 2, and that's 0.005. Now, what's the potential energy? We agreed that the potential energy at any theta is mgl into 1 minus cosine of the angle theta. And this is equal to 0.005. Now I just plug the numbers. So I have 0.5 for the m, right? How much is the m? 0.2, sorry. So 0.2 times 9.8 times 1 into 1 minus, or 1 minus cosine of angle theta is equal to 0.005. Okay, I need to get rid of whatever is here. So 0.2 times 9.8 times 1, this is 0.2 times 9.8 times 1, this is 1.96. 1 minus cosine angle theta is equal to 0.005. I need to get rid of whatever outside the bracket, so I divide by 1.96 and I get 1 minus cosine of angle theta is equal to 0.005 divided by that thing, and this gives me 2.55 e to the minus 3. Now I take minus cosine theta to the other side, so I'm left with 1 minus 2.55 e to the minus 3 equal to cosine of angle theta. 1 minus 255 e to the minus 3 is 1 minus 2.55 e to the minus 3 is equal to 0.9974. This is equal to cosine of angle theta. And now to get angle theta, I do shift cosine. So theta is equal shift cosine of 0.997 4, and this will give me, always remember, this will give me two values, plus or minus. So shift cosine 0.9974. This will give me plus or minus 0.007. Radian. Okay. Always remember we are dealing with radian. So we found the angles at which the kinetic energy is equal to the potential energy. Determine the magnitude of the maximum restoring force. So let's do it here, part F. Maximum restoring force. So F maximum equal to how much? F is M times A tangential. So Ft is M times A tangential. And that's equal to mg sine theta. Okay, so if I want the maximum, it should be m times g times sine theta maximum. Here you can use the fact that for very, very small values of theta, sine theta is equal to theta. So this is nothing but mg theta. Okay, so instead of sine theta maximum, I directly put theta maximum. Why is that? Because we have very small values of theta. And for that, the sine of the angle is the same as the angle itself. If you don't believe me, you just plug it in the mg sine theta and you will get the same answer. Okay. And this will give me, so F maximum, I use the calculator. This is equal to 0.2 times 9.8. Whether you want to put sine of 0.1 or just times 0.1, we will get the same value. So this is 0.2 times 9.8 times 0.1, and this is 0.196. Okay, I have just noticed that when I solved the exercise, I used 10 for G. Okay, this shouldn't confuse you. Here I'm using 9.8 for G in this video, but in the attached PDF, I have used 10 for G. Okay, so that usually we give you the value of G in the question and you use whatever that value is. Okay, so finally write an expression for the displacement angle theta t. So let me do it here. What does it mean, write an expression? So we have to say theta of t is equal theta maximum, okay, cosine, so this times cosine omega t plus phi. Okay, there are things we know and we can directly plug them. So I know, for example, that theta maximum is 0.1. So I plug it in radian and I've calculated my omega. How much is omega? It's 3.14. So I plug it. And now I have to get phi. Remember, to find phi, we use the initial conditions. And what are the initial conditions? That at t equal to 0, theta is equal theta maximum, which is 0.1. Okay, now I plug this in this equation over here. So theta at time 0, sorry, theta at time 0 is equal 0.1. So I plug it in this equation over here. So I say theta of 0 is equal to 0.1. I write this exactly as it is. It is 0.1 times cosine of 3.14 times t. But the t I'm using here is 0 because t I'm putting instead of t, I'm putting 0. Okay, plus phi, and this is equal from the question to be 0.1. Now implies How much is 3.14 times 0? It's 0. So I have 0.1 cosine pi is equal to 0.1 implies, okay, I divide both sides by 0.1. So I get cosine of angle phi is equal to 1. What is the angle whose cosine is 1? There is one angle whose cosine is 1, and that's phi equal to 0. So now what is theta of t? It's equal to 0.1. I plug this phi over here. So theta of t is equal to 0.1 times cosine 3.14 t plus phi, which is 0. So just like this. Okay, so this is the expression of the displacement angle theta of t. And with this, I reach the end. Actually, I have prepared to work on the first exercise, so I can just explain it and I can go through it very quickly, but I will be solving it slowly next time. Okay, so this is a problem from your booklet. It is not solved. This is exercise 15.3. A simple pendulum consists of a mass m equal 50 grams. So I have the mass. Okay, I have the mass. And string of length L. I don't have the L, so this is 0.05 kilogram. It's always good to change to proper units, metric units. L, I don't have. I mean to kilogram. L, I don't have it. The bob is displaced to the right by an angle of 8 degrees. So here they give me the angle in degrees. So theta initial is also theta maximum, and this time it's 8 degrees. To change degrees to radian, you multiply by pi and you divide by 180. Okay, and this will give you 8 times pi divided by 180. You just use your calculator. This will give you 0.139 radian. Okay, don't solve any problem in this chapter without changing to radian. Okay, and then it's released from rest. So I know that V initial is equal to 0. At the bottom of its path, it has a maximum speed of 0.441 meter per second. So we have V maximum is equal 0.441 meter per second. Use conservation of mechanical energy to determine the length of the string L. Here, since I have the V at equilibrium, so I will say mechanical energy at equilibrium is equal to the mechanical energy at maximum displacement. Because if I plug half mv maximum square here, which is half times m times v maximum square, I have all the numbers, it's equal to mgl into 1 minus cosine theta. I have the theta, I have the m, I have the g, then I will get my L. So this is how you get your L. Deduce the period of the oscillation. Now, since I have the L, okay, since I have the L, I know that the T is related to the L by 2 pi square root G over L. Since I have the L, I get the T. So now I get this one. I get the T. Also, I can get omega, by the way. It's always good to get omega because I'm sure you will be using it. Calculate the maximum kinetic energy of the bob. So we want the kinetic energy maximum. This happens when? This happens at equilibrium position, down, equilibrium position. And this is nothing but half mv maximum square, right? We calculate it. What else? Calculate the maximum restoring force. The maximum restoring force F maximum is mg sine theta maximum. We solved it in the previous problem, so I just plug the numbers here. Part E, write an expression for the theta of t is equal theta maximum cosine omega t plus phi. I have theta maximum, it's 0.139. I have omega, I calculated from t, and I want to get phi, but I have the initial conditions, so I can calculate phi from, I can calculate phi from the initial conditions, just as what I did in the previous exercise. And that's it. The last part, for what possible values of the angle theta, the kinetic energy and the potential energy are equal. So I say kinetic energy plus potential energy is equal, for example, one of these kinetic energies, one of these mechanical energies. I can either take mechanical energy at equilibrium or mechanical energy at maximum displacement or the maximum kinetic energy, whatever I want. So I say this is mechanical energy at equilibrium, which is half mv maximum square. Okay, now they're saying that the potential energy and the kinetic energy are equal, and I want the theta, so I have to keep potential energy. So now instead of kinetic energy, I will say potential energy plus potential energy is equal half mv maximum square. So 2 potential energy is equal half mv maximum square. So this is 2 times, what is the potential energy? It's always mgl into 1 minus cosine theta is equal to half mv maximum square. Okay, so what do I have? I have the m, I know the g, I know the l, I know the m, I know the v maximum, and I can calculate my unknown theta. Always remember, you will get 2 values for theta. One is positive, one is negative. I will be solving this exercise in the lecture for Thursday. Okay, so bye-bye for now. Yeah, just before the bye-bye. So I will be solving this problem for Thursday, but I'm giving you enough time to solve it on your own to see if you have really understood everything mentioned in today's lecture. Now, bye-bye.